Good morning, everyone, and welcome to the Philomathia Foundation at Berkeley Symposium, Pathways to a Sustainable Energy Future. I'd like to make a special welcome to those watching in the ballroom of the Shattuck Hotel and remind you that several of us will be over there to meet you in person at lunchtime. Our Chancellor, Bob Bergeneau, is not able to make it back from the East Coast to be here in person, and so he wants me to show you a video of his views on what the symposium can bring. And so let's start by showing you the video of Bob Bergeneau.
Good morning. It gives me very great pleasure to welcome you to today's symposium. This unprecedented symposium on energy and climate, bringing together leading international experts with UC Berkeley faculty and Lawrence Berkeley National Laboratory scientists, is one of the most exciting and important efforts that we are undertaking as a campus. It is an effort that we hope will set Berkeley on a path to making a distinct and defining contribution to solving the problem of energy sustainability, one of the world's greatest challenges. Energy and climate research are among our top priorities. UC Berkeley and Berkeley Lab have a combined energy and climate research portfolio that is very impressive. We believe that Berkeley can be a U.S. hub for energy and climate research and education. Our campus strategy, under the leadership of our Vice Chancellor for Research, Graham Fleming, is to bring coherence to all of the energy and climate research at Berkeley. It is our intention to educate the next generation of scientists, as well as policy, government, and industry leaders. We know that there is no silver bullet for a solution to sustainable energy. Challenges must be addressed through research that includes science, engineering, social science, and the humanities. Berkeley's unique comprehensive excellence, combined with that of Berkeley Lab, allows us to take on these challenges. We have a stellar list of leaders from the energy and climate research community participating in the symposium. We're also very honored to have my longtime friend, Ralph Cicerone, President of the National Academy of Sciences and world-leading expert on atmospheric chemistry, as our keynote speaker to lead off the symposium. I would also like to offer a very special thank you to two great friends and supporters of the university, Wilfred and Leslie Chung of the Philomathia Foundation, whose great generosity has made this major Berkeley event possible. I know that all of you, faculty, staff, the many students who are here, as well as our distinguished guests, are looking forward to a very stimulating and inspiring symposium. We are passionate at Berkeley about being responsible stewards of our planet, and with everyone's help, I'm confident that we will find pathways to a sustainable future. I wish you a very exciting and productive symposium. Thank you.
I think I would even go a little further than Bob Bergeneau and say that providing adequate, sustainable energy to the population of the planet is the defining problem of the 21st century. There's a scientific consensus that the Earth has entered a new geological era during which the evolution of the Earth's environment will be determined largely by what we do, by human activities, in particular emissions of carbon dioxide. Action taken this century will determine whether climate change is relatively brief or persists over many thousands of years. As Bob mentioned, this symposium marks the kickoff of a major focus on energy and climate at UC Berkeley. As always, our work at Berkeley campus is highly synergistic with that at Lawrence Berkeley National Lab, and we have speakers from both institutions today and tomorrow. What do we hope to get from the next 2 days? There are a variety of answers to this question. For everyone, an improved sense of the scale and depth of energy and climate research at Berkeley. For the faculty, I hope new ideas about how we can strengthen our efforts and increase our opportunity and impact and coordinate the whole of our research and teaching programs. For students, perhaps a better understanding that the energy problem isn't one problem, but a whole slew of interconnected technological and sociological challenges, and a sense of new ways to engage and be the leaders of a generation of responsible stewards for the planet. In this context, I want to acknowledge the terrific work of the Berkeley Energy Resources Collaborative, a student-led organization with 600 members. Finally, for our guests from government, industry, and the venture community, new ways to engage with Berkeley. We had an overwhelming response to this event, with over 1,000 people registering. This has required us to have 2 locations, here and another 350 people in the ballroom of the Shattuck Hotel. I will go over to Shattuck at lunchtime with our opening speaker, President of the National Academy of Science, Ralph Cicerone, Arun Majumdar, Director of the Advanced Research Projects Agency for Energy, ARPA-E, and Chris Field, Director of the Global Ecology Department of the Carnegie Institution, so you can meet them and ask them questions in person. A word now about how questions are going to work. We're going to take questions in both locations, and we're going to ask that you write your questions on cards, which will be collected by ushers, and each session chair will then select the questions to ask the speakers. After Ralph Cicerone's talk, I'll collect questions and ask him directly, and then we will go to a sequence of talks in which we will only take questions at the end, just before the lunch break. Putting on this extraordinary event required great generosity from quite a few people. To our keynote and kickoff speakers, thank you for your time and commitment. I know several of you changed important plans to be here. This symposium wouldn't have happened without the wonderful support of 2 great friends of Berkeley, Leslie and Wilfred Chung and their Philomathia Foundation, and we all owe them a great debt of thanks. Finally, of course, a huge amount of work is required to make something like that happen, and Tiff Drayson, Kaya Sert, and all of the development office at Berkeley worked heroically to bring all this together. So turning to our opening speaker, let me tell you a little bit about Ralph Cicerone. As I mentioned, he's the president of the National Academy of Sciences and the chair of the National Research Council. His research in atmospheric chemistry, climate change, and energy has involved him in shaping science and environmental policy at the highest levels, nationally and internationally. In 1999, the Franklin Institute recognized his fundamental contributions to the understanding of greenhouse gases and ozone depletion by selecting Ralph as the laureate for the Bauer Award and Prize for Achievement in Science. One of the most prestigious American awards in science, the Bauer Award also recognized his public policy leadership in protecting the global environment. Immediately prior to his election as the Academy president, Ralph Cicerone served as Chancellor of UC Irvine from 1998 to 2005, a period marked by a rapid growth in the academic capabilities of that campus. His research has focused on atmospheric chemistry, the radiative forcing of climate change due to trace gases, and the source of atmospheric methane, nitrous oxide, and methyl halide gases. And it's a great privilege to invite Ralph to kick off the symposium. So let's welcome him.
Thank you, Graham, and we'll send a videotape to thank Bob Birgeneau for the invitation to be here. It's really a pleasure. I'm very energized to hear about some of the research and teaching activities here at Berkeley on the topic of energy. I also want to thank the Chung family for their foresight and vision and commitment to high standards that make some of this work possible. It's very impressive. My title today is Climate Change and Human Usage of Energy, and I'm going to use a lot of slides. I thought I would start by giving you an outline. This is an outline of what I'm going to try to cover. First, the framework that many of us like to use in evaluating the forces on Earth's climate is that of energy balance. After discussing that briefly, I'll talk about greenhouse gases and the greenhouse effect. Then I'll switch into showing you some data on several major variables of climate: temperatures, ice amounts, and sea level. And of course, this is all connected to fossil fuel usage, and I'll talk somewhat about trends there. And then end by mentioning that to solve the energy problem requires attention to 3 constraints. Not just one, not just 2, and it makes the problem even more challenging. And I hope that this will lead up to some of the very advanced talks that we're going to hear for the next 2 days. Well, this first slide is obviously just a cartoon, but it's to illustrate the Earth's energy budget, if you will. Averaging over day and night in the course of a year, the Earth receives about 340 watts per square meter from the sun. About 1/3 of that is reflected from the tops of bright surfaces, 105 watts, not quite a third, like the tops of clouds and snow-covered features on the Earth, and of course anything else on the surface. We know that the Earth is not heating up terribly rapidly like overnight or cooling off as a planet overnight, so we know that there's a rough energy balance, so that about 237 watts must escape to space per square meter on an annual average, planetary average day and night. So that's roughly the energy balance. Now, the surface actually emits more radiation, nearly 400 watts per square meter, but due to interaction with absorbing and reabsorbing parts of the atmosphere, including clouds, the energy balance is the 237 watts net absorbed by the sun, mostly in the form of visible energy, visible light, and 237 watts escaping to space in the form of infrared planetary radiation for the most part. Now, these numbers are pretty well known, so these are not terribly mysterious anymore. But quite often, when the newspapers talk about humans causing climate change, they mention the burning of fossil fuels. So I've always wondered how many people actually think that it might just be the energy released by fossil fuel burning. So about 10 years ago, I just calculated these numbers, and just to try to make the point to people that the figure that I just showed, the energy absorbed from sunlight being about 237 watts per square meter, is about 10,000 times larger than all human energy usage, although today it's more like 9,000. When I first did the calculation 30 years ago, it was 13,000 to 1, but our usage is growing, of course. So on average, all the human energy usage on the entire planet, the burning of fossil fuels, that is petroleum, natural gas, gasoline, coal, wood, hydrothermal energy, nuclear power, biomass burning, you name it. If you spread that over the whole planet, we're releasing about 1/40th of a watt per square meter. Now, what you'll see in the next few minutes is that the extra heat trapped by the greenhouse gases for which humans are responsible is about 100 times larger than all the human energy usage. And for those of you who haven't thought about it, of course, when we use energy too, like to drive a car, we think of the directed energy that we get out of it, the translational energy, the movement of the car, but most of the energy is going into frictional heating, either through heating the engine and heating the air around it or the brakes. So all the energy we used is winding up like this, but it's still only 1/10,000th of the sun's energy coming in and 1/100th of the extra energy being trapped by the greenhouse gases. So that's just to put it on scale. Well, what about this greenhouse effect and this energy balance? If we assume that there's no time rate of change, we can write a very simple steady state equation that says that the energy coming in from the sun multiplied by 1 minus the reflectivity is equal to essentially the Stefan Boltzmann constant times temperature to the 4th power. This is essentially black body radiation approximation. What that means is that if we measure this quantity, the energy coming in, and we know the reflectivity, which is on average about 30%, we know this is a constant, we can solve for the effective temperature of the planet. And this calculation was probably first done about 30 or 40 years ago. And what happens is, if you do the calculation, you calculate that the temperature of the Earth is sub-freezing everywhere all the time, minus 18 degrees centigrade. Now, we know that that's not right. In fact, there's still argument over whether a large part of the Earth was ever frozen over at once. So the answer is wrong. And what's missing is the greenhouse effect, and the clouds are needed to calculate the surface temperature of the Earth correctly. Similarly, for Mars, we can do the same calculation because we know the distance from the sun to Mars, we know the average solar intensity. We can do the same calculation for Mars. And we get an answer which is essentially correct. It's about 28 degrees centigrade. That's minus 28 degrees centigrade, plus or minus day or night swings. And the reason is that Mars' atmosphere is so thin, the pressure is low, there are virtually no greenhouse gases, and this approximation works. However, for Venus, we underestimate the surface temperature of the Earth by several hundred degrees because there's such a thick atmosphere, high pressure, lots of CO2, and a very strong greenhouse effect along with clouds. So this is to show you that the greenhouse effect is not a wild theory. It's been operating in nature for a long time. It's part of nature. And I'll just show one of these graphs. That is the top one, just a schematic of the radiation of the sun graphed versus wavelength, the intensity of the radiation, where the peak lies in visible wavelengths, whereas the Earth, which radiates at a much lower temperature, not too different from room temperature, the peak radiation of the Earth is around 15 micrometers wavelength in the infrared. So most of this energy comes straight through the atmosphere, as I showed on that first cartoon graph, unless it's reflected by clouds, because there's not much in the atmosphere that absorbs visible sunlight. So the transmission is all the way to the surface of the Earth, which is what's shown on this very busy graph. Whereas the outgoing energy from the Earth, some of it is trapped and intercepted by infrared absorption features of ozone, 9.6 micron band of ozone. Where is it? I can't see it now. Here. There are a lot of CO2 lines and bands and many other greenhouse gases, but again, this is well known from laboratory work, from quantitative measurements. There are not too many mysteries. In fact, one of the first working scientific satellites which ever flew around the Earth in the early 1970s, this reference is from a 1972 paper, measured the outgoing long-wave emission from the Earth, that is infrared emission, as a function of wavelength. And this smooth curve is what the curve would have looked like if the Earth were simply radiating at 27 degrees centigrade, 300 Kelvin. Or if the Earth were radiating at 200 Kelvin, this is what the satellite should have seen. Instead, the actual instrumental measurement showed the presence of an absorption feature, the ozone, 9.6 micron band, and there are all kinds of features here, carbon dioxide at 15 microns and so forth. So it's actually more complicated than I'm illustrating, because the the wavelengths at which there is absorption simply means that the satellite cannot see all the way down to the surface of the Earth. There's too much absorption, and that the emitting parts of the atmosphere that are visible to the satellite are high up in the atmosphere where it's colder, so it looks like an effectively lower temperature of emission. But nonetheless, this is evidence of a real functioning greenhouse effect, which is quantifiable, and what we know now is that it's growing. I'm going to skip these chemical properties and simply go on to some data. Now, the iconic figure, the one that is most commonly known and acknowledged, is the carbon dioxide measurement set from Mauna Loa Observatory, which is in black, measured by Dave Keeling for nearly 50 years before he died, and is now being carried on by his son, Ralph Keeling, and also by one of our government agencies. The data set started in the late 1950s. Each one of these black dots, which are probably not too visible to some of you, but each black dot here is the monthly average of data that are taken approximately every hour from the slopes of Mauna Loa, Hawaii, well above direct pollution levels. The green data are from Antarctica. What you can see immediately is there's a seasonal cycle on the Mauna Loa data where the carbon dioxide goes up in the northern hemisphere fall and winter, and it goes down in the northern hemisphere spring and summer. Of course, it does the same thing in the southern hemisphere. I was just trying to be specific. But the other feature that you see is this underlying trend of growth, so that the initial values were measured at about 312 parts per million by volume, and the closing of this graph in the year 2009, 2010, the number is now closer to 390 parts per million. Similarly with atmospheric methane, What is not shown on this graph, these are atmospheric methane measurements from Ray Weiss's A-gauge project. He's at Scripps, but the data are headquartered at Georgia Tech. Show methane amounts, again, mole fraction in dry air. These are now parts per billion, so this would be 1.6 parts per million, 1.7 parts per million, and so forth, measured at several sites over the last 23, 24 years. What I don't show here are data from the 1950s and 60s and 70s, which were much more coarse, taken with a whole panoply of methods, but they showed numbers down around here. So there was a very rapid rise in methane amounts until about 1990. The annual rate of increase was about 1% per year. Since then, the rate of increase has slowed off, and in the last 2 or 3 years, it seems to be increasing again. But that's just to give you a feeling that there's another greenhouse gas which is increasing. Now, many of you know that one of the most important developments in this field and all of the earth sciences in the last 25 years was the extraction of ice cores from parts of Greenland and Antarctica. Ice cores being so long, basically cylindrical cores taken out of very, very deep ice sheets, that the ice cores go back hundreds of thousands of years. And by a number of dating techniques, that is assigning a date in history to the levels of depth on the ice core, either by measuring layers or by, when they get too thin and too compressed, other kinds of dating have to be done. But in any case, this set of data goes back from the present time, 0, 50,000 years, 100,000 years, 150, all the way back in this case to 400 and some thousand years. And the current version of this graph goes back to 600,000 or 800,000 years from Greenland. And there are several things plotted on this graph. On the upper graph is carbon dioxide measurements, with the carbon dioxide actually being extracted from the dated ice core. This is not an inference. This is a direct measurement of the concentration of carbon dioxide as a function of time in the gas that's trapped inside the ice core. And you'll see that at current, before the Industrial Revolution, the carbon dioxide concentration was about 260, 280 parts per million. In the previous ice age, about 20,000 years ago, the carbon dioxide amounts were about 180 parts per million. Then back to the previous interglacial warm period, where the amount went up to about 270 again, down to 180, 280, 180, 280, 180, back over the last 4 glacial cycles of the Earth. As far as can be verified, the Greenland ice cores show the same record with the same time history. Very interesting work can be done if you have high resolution enough in time to figure out whether the carbon dioxide leads the warming or lags the warming. That's a long story. But nonetheless, this shows that the natural range in which carbon dioxide has moved over the last 450,000 years is 180 to 280, never as high as we are now, 380 or 400, 390. Similarly with methane, where the natural range was about 1/3 of a part per million up to 2/3 of a part per million, 1/3, 2/3, and so forth. Whereas now we are about 5/3 parts per million of methane, just roughly. So there's also a proxy of temperature here based on isotopic contents of the ice, which gives the inferred temperature along with it. So what this tells us then is that the carbon dioxide and methane amounts seen now with contemporary measurements all around the world are higher than have been seen in the last 4 major glacial periods. Now, there's certainly inferences from very direct models of how much carbon dioxide there was in the Earth's atmosphere hundreds of millions of years ago in the Carboniferous, and there was probably more yet. But these are direct measurements, and they do extend back hundreds of thousands of years. Okay, those kinds of information and others allow us to say that the carbon dioxide increase that is seen now is from human activities. It is not natural. The approximate fractions are 85% due to fossil fuel burning and 15% from deforestation. And there are others here today who perhaps would argue with these figures, but I think these are as good as, they're consistent with all the data we have so far. Now, one of the ways that you can gain some confidence for that statement I just made is to compare the actual carbon dioxide measurements of the type I showed you with how much carbon dioxide should be accumulating in the atmosphere just due to the fossil fuel burning that we can account for and that we measure. And it turns out that on average over the last 40, 45 years, the carbon dioxide trend in the atmosphere is about 57 to, I'll call it 60% just to round off, of that seen from fossil fuel burning. So, as a scientist, you want to know where's the other 40%. But it does, if you step back from it and say, yes, this is partial evidence that the carbon dioxide accumulation in the atmosphere is due to fossil fuel burning because the numbers are very comparable, within a factor of 2. Now, the other kinds of evidence that pretty well ices it, that is, that proves that the carbon dioxide increase that's being measured now is due to human activities, is, well, I'm sorry, the time history of the carbon dioxide increase and that of fossil fuel usage, the 57% figure, factor of 2 agreement, I already said. That was this point, I'm sorry. The time history being that compared to ice cores from the 19th century and where we are now, it also mirrors the 2 order of magnitude increase in fossil fuels, more than 2 orders of magnitude. The fact that contemporary CO2 amounts exceed the amounts seen in previous glacial cycles, the geographical patterns of the atmospheric CO2 that we're seeing now, several kinds of isotopic indicators of the carbon isotopes in fossil fuel and what's being seen both in ocean surface waters and air. And then finally, what I just said, the same thing is true for methane and nitrous oxide. So there's virtually no remaining suggestion that the carbon dioxide increase is due to anything but fossil fuel burning and deforestation. Some of you will recognize this kind of a budget analysis of atmospheric methane releases now. The numbers, some of them are still very inaccurate. For example, the rice paddies one on which I've put a lot of time could be inaccurate by more than a factor of 2. But what is clear from other constraints, from isotopic constraints, from the rate of chemical take-up of methane in the atmosphere, we know that the total is about right. It's within 15 to 20% of being correct, and that the pie chart is shown about 2/3 human-influenced release of methane and about 1/3 natural releases of methane, such as natural wetlands, you know, where organic rich soils, waterlogged, become anoxic and anaerobic methanogens take over to release methane. Termites are certainly a part of nature, and so forth. So the message here is that about 2/3 of the atmospheric methane sources are under human control, or at least influence, and 1/3 not. And again, that gives you a nearly perfect agreement with the increase seen in atmospheric methane over the last few decades. So that then allows us to say, okay, we know the laboratory spectroscopy of these gas molecules. We know how their pressure broadening works. We know the Earth spectrum of planetary infrared being released. So we can calculate the extra energy being trapped in different layers of the atmosphere by the buildup of those greenhouse gases which are due to humans. And in this very simple graph, I show 4 categories. One is carbon dioxide itself, the radiative impact, the energy impact of the extra CO2 that is going from about 280 parts per million to 380 or 390 where we are now is equivalent to about 1.75 watts per square meter of extra power being trapped in the lower layers of the atmosphere. The methane increase, also caused by humans, is worth about 1/2 a watt per square meter. Nitrous oxide, I didn't show you data, but I have extra later. And then this category that I've labeled chlorofluorocarbons actually is a catch-all for chlorofluorocarbons, several of which are actually starting to decrease in concentration now because of the regulatory environment which is preventing their production and usage. But this number is still growing because of release of hydrofluorocarbons and hydrogenated chlorofluorocarbons, and also several completely fluorinated chemicals such as SF6, carbon tetrafluoride, and perfluoroethane. At any rate, these add up to about 2.6 or 2.7 watts per square meter, which you can see is more than 1% of the solar energy budget. It's more than 100 times what I said humans are using otherwise in the energy. So this is and this forcing is growing. It is not stagnant, it is not cyclical, it's growing. So it adds to concern. Okay, so much theory, so much of the extraneous stuff. Let's look at some climate data now. There are several sets of data which can be used or are being used now to calculate a global average temperature. This is a very simple concept. It's not necessarily the most useful, but it's an indicator of things that are happening. This set comes from the NASA Center in New York City under Jim Hansen, and 0 degrees on this temperature anomaly scale, 0 degrees is not 0 degrees Fahrenheit or centigrade, it's a reference point. In fact, it's defined to be equal to the average value of all the temperatures observed on the surface of the Earth in the period 1950 to 1980, a 30-year period. So 0 means the average of the 1950 to 1980 period. And you can see then the black dots are annual averages. The red curve is the running 5-year average drawn through the 1-year averages. And you can see that on this scale, starting in the 1880s, when there were enough data available to perform an appropriate geometrical global average, that the temperatures were generally lower, although a fair amount of variance, rising from the early 20th century to about the early 1940s, then a slight cooling, although it may not be statistically that impressive, until the late 1970s, and then more or less a monotonic rise in the 5-year average over the last 30 years. This increase in the last 30 years is outside the range of natural variability that was observed in the previous 100 years. It's leading to the highest temperature records that have ever been observed, and I don't remember the number, it's something like 12 of the 13 hottest years have been observed in the last 15 years, something like that, but I don't remember. Now, obviously, temperatures are not the same everywhere, so this graph simply breaks the data down into northern hemisphere, which is red, and southern hemisphere, which is blue. So some of you may remember that 2008 and 2009 were actually cool in the northern hemisphere compared to the previous few years, although still far warmer than the previous 100 years of the record. But the southern hemisphere, by contrast, set an all-time record in 2009. That this 2009 temperature averaged over the southern hemisphere was the highest ever. And if you go down into latitude belts and longitude belts, which I'm not going to stress right now, and into different monthly groups, you find that there's patchiness. Just as an example, even though Moscow had that terrible heat wave in August, they had had such a cold winter that for the first 7 months of 2010, Moscow was still a little bit below the reference period on this particular graph. So I'm just trying to show you that there's patchiness involved and that the years unfold differently each time. So 2010 right now is looking like it could be the hottest year of the 130 some years on record, but it really depends on what happens the next few months. The 2 hottest years up until now are 2005, the green, which got very hot in the last few months, and 1998, which was another very hot year, was a little cooler in the last few months. So we never quite know how these things are going to unfold. But to be clear, we should be using multi-year averages on data like this in any climatic application. Okay, those are air temperatures near the surface of the Earth, at the surface, over land and water. What about the water temperatures themselves? Well, the sampling of ocean waters isn't as frequent or as resolved as the atmospheric sampling, but nonetheless, there have been several workers in the last several years very carefully graph all with appropriate attempts, I think, at error analysis to keep track of the heat content of the upper oceans. That is, the oceans above the so-called thermocline, which is the mixed layer of the oceans, which on average is a few hundred, 700 meters of water. That is the water that's in contact with the warming atmosphere on a few years' time scale. And what one sees, this is a data set by Levitas, there's a couple of others that have come out recently, showing ragged but best fit of an increase in the heat content in ocean surface waters. This trend is about 4 times 10 to the 21 joules per year. And if you play around with the units and you take those radiative forcing figures I showed you a few slides ago, this one, if you multiply that all out by the surface of the Earth and figure how much it is per year, this number, that is the increase in the heat content of the world surface oceans, is about 10% of the extra heat trapped by the greenhouse effect, which is remarkably consistent with where we think the heat should be going. So these data on ocean surface and near surface water heat content also add more confirming evidence to the fact that change is underway, that the ballpark numbers are in very good agreement with the greenhouse calculations due to human-caused greenhouse effects. What about sea level? Well, maybe some of you here have measured sea level, but the method that was used for the first 100 years of this record was a fairly primitive one, but people were very, very careful in doing it along the coastlines of all the world's continents, that they would basically put geologically designed stakes in the ground and record water levels and different tidal levels, and then over many, many years create a record like this, so that this is average sea level graphed over the last 110 years, and that from 1880 to 1990, the rate of increase was roughly 16 centimeters in a century, or 1.6 millimeters per year. Well, the right-hand portion of this graph is red ink, and that is the most recent 12 or 15 years when Earth orbiting satellites with ranging devices have been used to measure sea level much more accurately, much more densely, so that we should be getting a better reading of an appropriate global average, because you may know there are geological differences in different parts of the world where the land itself is rising or subsiding, so that you don't expect to see exactly the same answer everywhere. Well, here's what the most recent record shows from 1992 to into 2009 of the Earth orbiting altimetry devices, some American, some French. First of all, we're getting a much better measurement of sea level in terms of accuracy, precision, and frequency of measurement. But the trend that's being measured is a little bit more than double what had been seen before. Now, when the first few years of these data came out, I don't think anybody was convinced that sea level rise is accelerating, but there is now some reason to say, yes, it does seem to be accelerating, and I'll show you that next. So the current rate of rise observed is a little over 3 millimeters a year, 3.3. And even that, there's a slight seasonal variation. Well, what about ice amounts? Because until just 5 or 6 years ago, it was not possible to say why the sea level rise was what it was, a little bit less than 2 millimeters a year. Now it looks like there's some closure to the arithmetic. these are a set of data from an Earth orbiting satellite which responds to very small perturbations in the Earth's gravitational field. Now, if the Earth were perfectly spherical and the matter was distributed perfectly uniformly, these satellites wouldn't work. But these satellite sensors, and it's very complicated, they're very high tech, and I'd love to talk about how they work, but we can't do it today. They use a whole fleet of sensors where the satellite positions are linked with each other through K-band interferometry. But they keep track of each other, and as one satellite goes around the Earth and it senses, say, a mountain range beneath it, there's a slight perturbation, a slight acceleration in its motion, and the second satellite can sense it, and then the second satellite following encounters the same perturbation, and after enough orbits, they can actually detect if there's a time rate of change of the amount of mass below as a function of geography, that is, wherever they are. Well, this data set was released in 2007 or so, for the first 3 years of measurements of this so-called GRACE gravity satellite looking down at Greenland. And it showed that the Greenland mass, the Greenland ice, is losing mass at about 160 cubic kilometers per year. But one criticism of these data, well, you know, look, it's only 3 years. These measurements have never been made before. So it was a tremendous demonstration of the value of this instrument. But last year, Isabella Vellaconia updated the data. It's now a 7-year data set. She's a physicist by education. She's in my home department at UC Irvine, as a matter of fact. But the data are now a 7-year record, and the best fit to the data are no longer a straight line declining. They are now, the best fit is, as you can see, an accelerated rate of ice loss, so that averaged over the 7-year period, and once again, averaged over the 7-year period, the rate of loss is 230 cubic kilometers per year, where the trend at the end was really more like 285 gigatons per year as something that was less than half of that when the data set started. So there is evidence of an acceleration, and the contribution to sea level rise from Greenland alone is, at that average value, is about 0.6 millimeters per year. If you take it at the current value, it's probably more like 0.8 millimeters per year. And the same thing is seen over Antarctica. And this satellite instrument is good enough that they can separate West Antarctica, East Antarctica, Northern Greenland, Southern Greenland, and so forth to see that these, how the trends actually show. So the rate of loss of mass of ice over Antarctica is now equivalent to also about 0.8 millimeters per year of sea level rise. So now we can do a closure on what's causing sea level to rise. It is definitely what was suspected back in the early 2000s, that the expansion, the thermal expansion of the surface waters caused some of the rise in sea level itself due to the increased temperature and heat content. There is certainly a loss of continental glaciers. I'm not showing you any data on those today. But the new player here is Greenland and Antarctica, that the losses are quantified, they're shown to be accelerating. Now, some of you may have seen aerial photographs of Greenland, and you get the feeling that this research is being done with sextants and cameras. That is no longer the case. These measurements are really beautiful remote sensing. And I must say that this detection of this amount of, this rate of loss over Antarctica and Greenland by Isabella Vellaconia and her colleague John Warr actually only confirms what had already been measured with a completely independent technique, a radar ranging device, which measured the height of the ice over both surfaces, and then doing a surface integral calculating the rate of mass loss. So I think these numbers are solid because they do confirm what had already been independently deduced from another method. So going back to the temperature record that I showed you of surface temperatures, I kind of implied to you that there's something unusual in this last 30 years. It certainly looks like it. It's out of the range of previous variability, and it's more or less monotonic if you average over 5 years. But there's, I think, oh, there's one more thing I want to say, yes. That the physical principles do explain this warming through the greenhouse effect. And that quantitative calculations with the most up-to-date and the most complete models also demonstrated. It's not just a hand-waving qualitative statement. These measurements are from a UK climate modeling group where they attempted to say, look, if we run these first principle models of climate change and calculate global averages, do we get something like what is measured? And the green graphs are their model calculations. The black is the temperature record of the kind I just showed you. And the answer is no, that they get a lot of variation, but they don't get this kind of a continuous rise. It's only when they include this additional greenhouse effect that they can reproduce the temperatures of the last 30 years, which is what I've been implying. Now, there still could be other explanations, such as it's been just again and again and again, people say it's the sun that's causing the warming. I know that's where I was some years ago. I was hoping it was true. I thought it would be kind of interesting. But now we have enough measurements of the actual rate of arrival of sunlight energy. Those of you who are good at arithmetic will see that this number is about 4 times 342 watts per square meter. That's because of a geometrical conversion from the energy arriving and striking a plane to a spherical geometry. So this number should be 4 times the one I showed you earlier, about 1367. But the point is, what is actually measured over the last 30 years in the rate of arrival of solar energy is that the graph is basically cyclical with an 11-year cycle. This last solar cycle was unusual. It's going up now. But you do not see an upward trend in the amount of energy being received from the sun. Instead, we see something that's cyclical. So we are now in a position to say that that particular explanation for the changes of the last 30 years is no longer tenable. Now, could there be something wrong with this record? I suppose so. But I've read the papers. I've seen the kinds of work they've done with the data. I think there is no evidence for the kind of increase in solar luminosity that might disable this explanation. So the point I'm making is that the greenhouse effect calculations do end up to be compatible with the observations. Another explanation that would have been a nice one is that the sun itself is releasing more energy fails. So now let's switch to energy. In the meantime, what has been going on with human usage of energy? And I know that we're going to have several good talks in the next 2 days that will show both on the demand and supply side very different ways of looking at these numbers. But one set of data I like happens to come from one of the branches of the Department of Energy, the Energy Information Agency. And they show that in 1970, world energy usage was about 207 quadrillion BTUs. Now that's a terrible unit, I know. We really should switch to metric units, but these are the units that the Department of Energy still uses. 207 quads. That number had doubled by about the year 2002 to about 415, and these data are historical before 2008, and then are projections beyond 2008. So you can see two things in this graph. These are actual energy consumption data, that the consumption had more than doubled over the last 35 years, that the projected rate of energy demand and usage in the next 25 years is further growth, and the breakdown of the red parts of this graph are transitional and emerging economies, whereas the blue part are the mature market economies. So in the past, the mature market economies like the United States and Western Europe and Japan, Canada, were the bulk of the energy usage. But as you go forward, the growth in the red-coded countries grows, And the projected growth in the future, which could be on the conservative side of almost 3% per year in the emerging economies and transitional economies, and something closer to 1% per year of the mature market economies. So this leads to all kinds of difficulties in how we're going to go about dealing with the situation. But just to illustrate one aspect of this demand, this table shows a projection from the year 2006 from the EIA again of the increase in coal-fired electric power to be expected in 3 countries, the United States, China, and India, and then the world. So that these figures before 2010 were historical, and everything in the future was projected ahead. So the United States, for example, was supposed to increase by 3%, 310 gigawatts of coal-fired electric power in the year 2003, up to about 319 in 2010, whereas China was supposed to increase roughly 50% in that 7-year period, and so forth. Well, things have been happening faster than that. So in the year 2008, the Department of Energy, EIA, altered their projections based on what had been happening, and the new projection for China coal-fired electric power is not 348 for the year 2010, but instead 478. And for the year 2020, the projection is 756. And for what it's worth, the projection for 2030 is 1,000 gigawatts. So the demand is growing. Now, I come to the 3 constraints topic that I mentioned. In dealing with each other, individuals, groups, businesses, governments, most of those people understand that there are 2 ingredients that are needed for us to have a stable and desirable energy situation. One is to keep the costs down. Everybody understands that, from homes, hospitals, governments, and the other is domestic security. Every country wants to have a form of energy accessible to it, which not only can be afforded, but is secure. And this particular quote, I'm sure many of you watched Boone Pickens on his campaign the last year and a half. One of his quotes that he focuses on is the danger of relying too greatly on imported oil. And he calculates, I think this was at 130 or $140 per barrel. That was the outflow of US dollars per year. The point I'm trying to make here is that many people who we deal with, including ourselves, understand the cost constraint and the domestic security need, and this is true all over the world. The third constraint, the third ingredient that we need, the climate constraint, is not yet well understood by most people, whether in businesses or governments. So when you look at the very strong rate of growth, though, in fossil fuel carbon dioxide emissions, and get any guidance at all from what our disturbance to climate is going to amount to in the coming decades, it begins to look more serious. So this set of data simply shows as is labeled, the global fossil fuel carbon dioxide emissions measured in carbon only, historically, and on this scale, you could not even see the first billion tons until early 20th century. Now we're up to a figure which is around 8 billion tons of carbon emitted this way. And to illustrate it in a more cartoonish way, this is from some Japanese colleagues who illustrate the imbalance in the Earth's carbon handling or carbon cycle with a bathtub. So the rate of input, now I just showed you it's more like 8 billion tons of carbon a year, but they used 7.2 in this old cartoon, illustrated as water coming in, whereas the natural drainage rate is only about 3 billion tons a year, and that's with over decades of measurements of oceanic uptake of CO2 and of land uptake of CO2. The number turns out to be about 3 billion tons a year, so there's an imbalance of at least 4 billion tons a year, and if this number is 8, as I just showed, then the imbalance is 5. And if deforestation is another 1.5 or 2 billion tons a year, then the imbalance is something like 9.5 or 10 minus 3 or 6.5 or 7 billion tons a year. So it's a large imbalance. What that means is the rate of water in the bathtub continues to rise, and it will continue to rise until the rate of input is decreased down to something of the natural absorption capacity. Now, actually, the most quantitative way of estimating this absorption capacity of carbon dioxide measured in carbon is through atmospheric oxygen measurements. Some of you know that Ralph Keeling at UC San Diego and Mike Bender and others at Princeton have been measuring the decline in atmospheric oxygen. And by those measurements and a couple of other inputs, they can calculate numbers like this completely independent of the other measurements that had led to the same number. So this balance is pretty well known. Now, what do we have to do to get back, if we had a desire of stabilizing the carbon dioxide amounts in the atmosphere? It shows that the emissions would have to be cut by multiple billions of tons of carbon per year. And these kinds of calculations simply say, okay, here's the historical rise of the rate of fossil fuel use. How could we attain various levels of carbon dioxide by cutting back on the CO2 emissions? The challenge is huge. Just to illustrate it, there was a very good set of papers by Rob Socolow and Steve Pacala several years ago, which tried to show us what the scale was. There's so-called carbon wedge papers, where if one had the goal, for example, of stabilizing atmospheric carbon dioxide at 500 parts per million, including other greenhouse gases, then the emissions have to be 7 billion tons a year below the business as usual in the coming decades. And to do that, avoiding 1 gigaton carbon per year emissions would require things like the following: that energy usage in every building on the surface of the Earth would have to be cut 20 or 25%. Or another way to get 1 billion tons of carbon per year emission would be that the fuel economy of 2 billion cars would be doubled from, say, 30 to 60 miles per hour per gallon, or that carbon capture and storage would have to be employed effectively for 800 gigawatt coal-burning power plants, or something similar. 700 of the right size nuclear power plants would have to replace those coal-fired power plants. You get the picture. That each of these achievements would reduce the emissions of carbon dioxide by 1 billion tons of carbon per year. And we're looking at the need to decrease those emissions by multiple billions of tons per year. I won't belabor this anymore. Now, on top of the climate problem, we have the issue of the decrease in alkalinity of the world's oceans caused by the uptake of the carbon dioxide. That it's relatively simple to calculate what the pH of ocean waters will be doing as carbon dioxide is added. The pH, the average pH of world's oceans has already dropped about 1/10 of a pH unit. That is, it's become more acidic already, and just adding more carbon dioxide will do more. Now, this kind of acidification I don't think anybody knows how to predict what the marine biology, the marine ecology impacts will be. Very difficult to imagine how we will avoid this kind of increase in oceanic acidity. It's just something else I should mention. So where do we start? I want to close on energy efficiency, because energy efficiency can address all three of those needs, all three of those constraints that I mentioned. Cost that everybody understands, domestic security that everybody wants, a domestically secure energy supply, and slowing down the emission of CO2 and methane in this case. If you think about energy efficiency, and many of you in this room do it all the time, first of all, that statement is true for any country. It would decrease their dependency on foreign oil. It would improve national security. It would decrease a trade deficit. It would decrease local air pollution due to the fewer combustion products. It would increase national competitiveness to the extent that the cost of energy is embedded in manufactured products and services. It would encourage development of new products for global markets, some of which will be discussed in the next 2 days. It would decrease household energy costs and also slow down the increases of carbon dioxide and methane. So you would think that seizing upon the gains of energy efficiency would be a no-brainer that everybody would agree to get on with, and I think people are now beginning to understand why it's not happening as fast as everyone wanted to. I'll close with an understatement. I don't have any more numbers to show, but clearly energy efficiency won't get us all of the way. There is an enormous need for breakthroughs, especially in science and technology, to provide more efficient and the right kind of energy, and we're going to hear more about those in the next 2 days, and I will stop after that introduction. Thank you.
Cards are being collected. Let me start by asking Ralph one question. Some very radical approaches are being discussed involving geoengineering. Seem very scary to me. Would you like to give us your view on what could be achieved by large-scale changes in the way the planet absorbs or radiates?
It's tempting to look for ways to manage climate change. Okay. But there hasn't been much research done, and here I'm going to make a plea for research because I don't know of anyone who wants to go out right now and try a large-scale intervention. For example, dumping colossal amounts of iron into the world's oceans to try to stimulate photosynthetic uptake of carbon dioxide. You know, there have been some experiments done, a lot of good thinking. Another idea is to load the stratosphere with brightly small sulfate particles which can reflect sunlight, visible sunlight, back out to space. This has been discussed. Very little research has been done. There was a fantastic paper, in my view, that just came out this week on an idea of engineering various shapes and material particles which could be levitated photophoretically into very high levels of the stratosphere that might be more efficient than the sulfate. The point is, we're waving our hands, and no one I know wants to try large-scale implementation, but more people are being tempted to start thinking about these solutions. So I think what we need is to treat these ideas as if they were just normal science. In other words, you come up with a concept, you try to quantify it, do quantifiable calculations, publish them in journals, peer-reviewed. The bad ideas will be sifted out. Any ones that survive the early calculations can be advanced. And in the meantime, I think all of us should agree that we should probably not try any large-scale interventions yet because of potentially unknown side effects. So that's a long-winded answer, Graham.
Thank you. What is the basis for projections of coal capacity in China?
Some of you here probably know better than I. The Energy Information Agency at the Department of Energy is a fairly conservative outfit that bases their projections largely on current trends. And that is how many coal-fired power plants are already being brought on per year in China and how this would be extrapolated in the future given other measures of demand for electricity and coal supplies. I don't think there's any large sophisticated econometric modeling that goes into it. I think it's largely extrapolating of trends, but somebody here might correct me.
I think, given the time, we should move on, and I'll do that by asking Don DiPaolo, Professor of Earth and Planetary Science and Director of the Earth Science Division at Lawrence Berkeley National Lab, to come up and take over as chair of the next session.
Thank you, Graham.
Yeah, let's thank Ralph one more time.